Welcome to this presentation. My name is Mark Zithian. The date today is May 29, 2025. So this presentation is going to focus on solar plasma versus solar electric. So we first have to identify the states of matter, which most are familiar with gas, liquid, and solid. But the most abundant matter, or the fourth state of matter, is known as plasma. And we'll explain that in a second. And then, of course, we have gel. So there's actually 5 states of matter. And so as you enter physics, engineering, STEM coursework, undergraduate, graduate, PhD level, then you're used to knowing the states of matter as being 5-fold: gas, liquid, solid, plasma, and gel. So what gas, liquid, solid, and gel have in common is that they are in the material state, moving slower than the speed of light. However, when we get to plasma, plasma is the fourth state of matter. However, that is matter moving at the speed of light, so then it becomes a medium of photons or wave particles. This is also relevant to magnetic fields as well. So if we were working with the waveform of, let's say, electrical power or the waveform of magnetism, we would be working with light. And if we work with a particle form of magnetics, then we would have actually electricity. So all three are interconnected. So next we have the fifth state of matter, which is also the fourth state of water. This is known as structured water, and this makes up between 80 and 96% of all biological material. So this is also known as biological gelatin, or just jello that you make in the refrigerator. That is the derivative of what biology is derived out of: the crystalline structure of water made into a semi-solid type of material known as the gel state. So now we'll go back to the solar plasma versus solar electric concept and comparison. So here we have a sun, and we can identify the amount of DC electrical power we can extract from 1 square meter of sunlight, 350 watts on average, between 3 and 500. But that is sourced from 1,000 watts per square meter of solar thermal or solar heat power. So that's what your solar panels do, is they convert the solar thermal power into solar electric, and then create an electrostatic or an electricity stopped type of an electrical potential, for which, when grounded, then becomes electrodynamic, or moving electrical power or electricity. So now we have to take a break from that concept, shift gears to comparing solar plasma to the Hiroshima and Nagasaki nuclear detonations. So just an idea about the plasma involved in the Hiroshima and Nagasaki nuclear detonations. We'll use these because they are not theories, they are not theoretical physics, but there's actual practical applications for which these detonations, their power was measured at approximately 63 trillion watts of power per detonation. So we can access the Einsteinian relationship between energy and matter. This is called special relativity, and it also sources from the experiments Rutherford and James Maxwell Clerk, the field equations of Clerk in the late 1800s, then morphed into the work Einstein was working on, the research Einstein was working on. So we could say it's a Maxwell, Planck, Rutherford, Einstein research continuum that led to E is equal to mc squared. So we'll just call it Einsteinian special relativity. So we can take our E value because we want to take the energy outside of time. So instead of joules per second, 1 joule per second is 1 watt. We can just take 63 trillion joules, 63 times 10 to the 12th power joules, and make this equal to m times the speed of light, 3 times 10 to the 8th power meters per second, quantity squared. And then we can just solve for m algebraically. So we calculate 0.0007 kilograms of plasma mass accelerated to the speed of light yields or equals 63 trillion watts of power. So there's much more of a feature in the harnessing of energy with respect to plasma than there is probably any other conventionally available source. So of course, we could harness much power at a low cost from nuclear electric sources or even plasma charged particle accelerators, which we already have cyclotrons everywhere. But then again, this then defeats the purpose of cost-effective, easy to produce or harness, available energy for all. Of course, the big energy monopolies will not like this idea, which is why they don't really like you to know about plasma, the fourth state of matter, until you start studying electrical engineering or mechanical engineering, or you get into you major in physics or chemistry, or you go into computer science, operations research, you go into the STEM disciplines. Then you're very intimately familiar with the fourth state of matter, also known as plasma. But the thing is that, is it easily accessible, and can we make it safely with minimal risk and cost? And the answer is, well, if the infrastructure was set up accordingly, we could work on the research to convert sunlight into plasma, because just 0.7 grams of mass accelerated to the speed of light will yield 63 trillion watts of power. But hold on now, we only have 1,000 watts of power at the most to harness sunlight energy into any type of power or storage potential, energy storage potential. We'll call it potential energy storage capacity. So the goal should be to convert sunlight into plasma, which is our applications on spacecraft, but tends to be shrugged away as a impractical application on the Earth's surface. However, whenever we put more attention on a concept, we make breakthroughs, and what once was impossible or difficult or expensive becomes very easy, cost-effective, normalized, and abundant. So we have to put more attention probably into converting sunlight into plasma, even if it is a kinetic storage system with plasma particles moving at the speed of light within a substrate. Because after all, you can only get 1,000 watts of power per square meter of sunlight exposure. But where the breakthrough would occur is that there's going to be a higher energy density storage potential per unit mass. So just to elaborate on that concept is let's say you have a pound of crude oil. This will contain approximately 20,000 BTUs per pound of potential energy as its energy density. So if we multiply that times 1056 joules per BTU, we calculate 21,120,000 joules per pound. So if we were to divide that into 1 over 2.2, that comes to 46 megajoules per kilogram is the energy density of crude oil or any type of hydrocarbon oil. We have different densities in fuel, so of course diesel weighs more per gallon than kerosene, and kerosene weighs more than gasoline, but if we equalize them all into an average density, then they all have 20,000 BTUs per pound derived from their crude oil source. Now, if we compare the average solar panel taken from a low value of 300 watts DC to 500 watts DC, if you have very high-end solar panels, we have an average DC electrical power value for each solar panel of approximately 350 watts. So 1 watt is 1 joule per second, so we take it outside of time. An average weight of a solar panel is 40 pounds. So we could take 350 joules and divide this into 40 pounds. Each solar panel only has an energy density of 8.75 joules per pound, but we then take that value into 1, divided into 2.2. So each solar panel has 19.25 joules per kilogram. And each solar panel has 19.25 joules per kilogram, whereas crude oil has 46,464,000 joules per kilogram. So that means one pound of crude oil has 2.4 million times more energy density than one solar panel. Or we'll just say overall, crude oil has 2.4 million times more energy density compared to solar panels. And at least 30 to 40% of solar panels is made out of crude oil required to make the plastics and the epoxies, etc. So one would say, why not just increase the compression ratio, control the detonation, and completely vaporize, combust, and reheat hydrocarbons into plant food, carbon dioxide, and water vapor, which is what we're doing now in cars, gasoline combustion cars. And then we have just an equal amount of environmental hazard by making electric cars because of the emissions as you're isotoping carbon-6 into other isotopes, carbon-14, carbon-21, to make these exotic electrical plastics and shielding systems. So you're also leaking into the environment traces of what would be not necessarily oxides of nitrogen and oxides of sulfur, but other trace isotopes into the environment. So the amount of environmental hazard is minimized and equalized across electric and gas vehicles because of the way they're built. So that's the physics and chemistry involved. That's just what it is. And so we can calculate that. Why would anybody invest in energy sources that are 2.4 million times lower in energy density but expensive on the level of $300 per 40 pounds versus $3 per 1 pound. So you're looking at a cost that's about 40 times higher in comparison ownership of the energy source. So the goal is to increase the energy density, the storage capacity per mass. So if we instead went to what we'll call the future concept, a plasma battery, because one does not exist on the level of the innovative goal, but we'll say it's a engineering pursuit. Engineering is concerned with technologies that have not yet been created, research engineering. So we'll call it a quote unquote plasma battery. This would be exponentially greater in holding a potential energy charge than a traditional solar panel. And it is because of the concept of solar plasma, extracting plasma from sunlight into some sort of static or dynamic storage medium. We'll call it a plasma battery, probably a dynamic plasma charge capacitance in the form of a plasma battery. And then you keep charging the so-called theoretical plasma battery until enough plasma particles build up to whatever the material structure can handle. So you might be able to charge 2 or 3 million watts of power in a plasma battery and then run an electric car for as long as 30 days before perhaps 1 day of charging is required to replenish 30 days worth of driving potential energy. So that's the main takeaway, to have a system of harnessing sunlight into plasma and then storing plasma in perhaps a electrokinetic medium we can call a plasma battery, perhaps even fiber optics charge capacitance, keeping the particles moving at the speed of light within the battery. And then again, you're not getting more power out of the system, but you're getting much greater storage capability. So then eventually a 50-pound battery can replace a 2,000-pound battery. So that is what is meant by increasing the energy density. And if this is improved upon, then the theoretical plasma battery may have as much or even greater energy density than crude oil. And then after that, the entire system has to be mass produced, made cost effective, and then there could be various at home or at factory or at dealership charging mechanisms, either from the sunlight itself. And another breakthrough would be converting electricity into plasma. That's another application. And if so, then you could use your electrical power instead of the sun to charge a plasma battery. So remember, this is going to open up more innovation. But when you solve problems too quick, you can collapse the economy very, very fast. And people in the big business of energy and utility corporations will absolutely fight tooth and nail to not let some sort of technology like this out. Because even if it does, quote unquote, save the world, it will bankrupt the leading economic centers. So again, there's a time and a place, but in the mind of the physicist, the chemist, and the engineer, this is the best way to go about extracting higher energy density from sunlight into a kinetic plasma fiber optic type battery. So the main takeaway of this presentation is solar plasma, if harnessed, then many times more power can be harnessed compared to traditional solar panels. Thank you for watching this presentation and have a great day.